Hello, in this video we're going to introduce the idea of power series and talk about the rays of convergence of the power series. We'll work with power series for the rest of our study of infinite series. Power series are related to the Taylor series and Taylor polynomials, which we will be discussing in later videos. So in previous sections, we've worked with the geometric series. That's a series of the form 1 plus x squared plus x cubed, etc. This is the geometric series with first term 1 and ratio x. We know this series converges to 1 over 1 minus x, provided x is strictly between minus 1 and 1. Now we can think of this series as defining a function with domain between x from minus 1 to 1. When x changes, of course, the sum of the series changes. A series of this form is also called a power series. So let a be a fixed real number and let x be a variable. A power series centered at a is an infinite series of the form a0 plus a1 times x minus a plus a2 times x minus a squared, etc. So we see it displayed right here. And of course, we can write that in the summation notation as the sum k runs from 0 to infinity of akx minus a to the kth. The coefficients a0, a1, a2, etc. are real numbers, so they usually take on numerical values. In particular, in a power series centered at a, the variable x only occurs in terms of the form x minus a. So let's look again at the geometric series, which we talked about earlier in this video. This is an example of a power series centered at 0. In fact, we can think of the x, or x to the k, as x minus 0 to the kth. And so this is a special case of a power series. All the coefficients in this series are equal to 1. And we know the series converges if minus 1 less than x less than 1. Now, for a given power series, a0 plus a1 times x minus a plus a2 times x minus a squared, and so forth, we're going to try to answer two questions. First, for what values of x does the power series converge? Again, as we saw up here in the geometric series, this series does not converge for all x. It only converges if x is between minus 1 and 1. A second question we might ask is that for the values of x for which the series converges, what is the sum of the series? In this video, we're going to see how we can answer the first question, and we'll see that the convergence set is always an interval centered at a. So we'll illustrate this with an example. Let's find all values of x for which the power series, summation k runs from 1 to infinity, minus 1 to the k, x minus 3 to the kth power over k times 4 to the k converges. So we're going to find what's called the interval of convergence for this series. And with that will come a radius of convergence, which we'll define in context. So because some terms of this series might be positive and others negative, we have to be a little careful. With the minus 1 to the k power and the different values of x, we cannot predict the sign of any term. So as we saw in section 10.6, when we studied alternating series, one of the options in such a case is to consider the series of absolute values and see if that series converges. So what we've done here is we've taken the power series we're concerned with and replaced it by the series where we've taken the absolute value of every term. And with the absolute value signs, the minus 1 to the k becomes irrelevant. And so we're really looking at this slightly simpler form. Now, this series now has non-negative terms. So we can use a test for series of non-negative terms to investigate the convergence. And given the form of this test with all those powers, it makes sense to consider something like the ratio test. So let's take a look at the ratio test. The ratio test says we want to take the ratio of the k plus first term of the series to the kth term, so ak plus 1 over ak. And so here the ak represents the general term here, not just the coefficient. So the term of the series, the kth term is down here. We can just pick that out of the series we saw here. And Then replacing the k by k plus 1 gives us the numerator up here. And then we do our usual algebra to determine this limit. We first of all pull off the part that come from the k expression down here. That leads to this part. Here's the 4 to the various powers grouped together, and here are the x minus 3 powers grouped together. Again, as we saw earlier, writing things in this way allows us to better see the cancellation, the algebra we might use, and this thing comes out to be absolute value of x minus 4. Now remember that according to the ratio test, a series of non-negative terms converges if this ratio is less than 1. So we can declare that the convergence will be the case if we know that x minus 3 over 4 in absolute value is less than 1. So let's start by assuming x is such a value to make this inequality true. In fact, we can solve this inequality, multiply by 4, get rid of the absolute values. This says x minus 3 is between minus 4 and 4, and then add 3 to both sides, and we see these are the x's for which the ratio turns out to be less than 1. Now, from this form, this 4 here is important. The fact that x minus 3 is less than 4. This 4 is called the radius of convergence of the series. Now, the ratio test also gives us information about divergence. We know by the ratio test the series diverges if this ratio that we came up with is bigger than 1. So let's analyze that case also. So as x minus 3 over 4 bigger than 1 means either x minus 3 is less than minus 4 or x minus 3 is greater than 4. And so we have these two options, x less than minus 1 or x greater than 7. Now, remember, as we discussed with the ratio test and the root test, that when a series diverges by the ratio test, it turns out that the terms of the series don't even go to 0. So in fact, such a series also diverges by the nth term test. And if we remove the absolute value signs, those terms still do not go to 0. And so even without the absolute value signs, the power series will diverge for those values of x. Now, the one time the ratio test doesn't help us is when the ratio is actually equal to 1. So we've got to keep track of that case too. We have no information when the ratio is 1. That is if x minus 3 and absolute value over 4 is equal to 1. And solving that equation, we find that we have x equals minus 1 or x equals 7. So to summarize, we have a pretty good idea of the values of x for which the power series converges and the values of x for which it diverges. So there are only two values of x, minus 1 and 7, for which we do not yet know the behavior of the power series. So this is our information so far. The red indicates divergence, less than minus 1, greater than 7. And we have convergence if we're strictly between minus 1 and 7, as we see here. Okay. Now, let's see if we can figure out what happens at minus 1 and 7. And to do that, we're going to do that simply by plugging x equals minus 1 and then x equals 7 into the original power series, and then seeing if we can determine whether the resulting series converges or diverges. So we'll take x equals 7 first. So we take the original power series, the absolute value signs are once again gone, and we plug in x equals 7, which leads us to this form, and 7 minus 3 to the k is 4 to the k, which leads us here, and once the 4 to the k is canceled, we're left with this result. And if we write out a few terms of this series, we see it's an alternating series. The minus 1 to the k power gives us the minus plus alternation we see here, and the terms are of the form 1 over k, they're decreasing. So by the alternating series test, this series converges, and so that tells us the power series converges for x equals 7. If we plug in x equals minus 1, again, the original power series without its absolute values, we plug in minus 1 for x. we get a minus 4 to the k power on top, which we can split into minus 1 to the k and minus 4 to the k. And then these two powers of minus 1 multiply to give 1. The 4 to the k's cancel. And we're left with this very familiar series. Of course, you recognize that as the harmonic series, or if you like, a p series with p equals 1. We know this one diverges. So this tells us the power series diverges when x is equal to 1. So our conclusion then looks like this. The power series converges for minus 1 less than x less than or equal to 7. So we have filled in this blue dot here, denoting the convergence at 7. Filled in the red dot, indicating the divergence at minus 1. Now, once again, this diagram tells us we have radius convergence of 4. To get the radius convergence of a power series, you go from the center point, the point of expansion, out to either edge, and that distance is 4, and that distance is called the radius of the power series. And so we have radius 4 in this case. So some things to remember. A power series centered at x equals a has the form we see here. Kind of looks like a polynomial in powers of x minus a. Often it's useful to think of power series as just infinitely long polynomials. The coefficients will be numbers generally, a0, a1, a2, a3, and they will probably depend on k, so different coefficients as we take different terms of the series. And of course, x is a variable. If a power series centered at a has radius convergence r, then the power series converges absolutely for x such that x minus a in s value is strictly less than r. That is for a minus r less than x less than a plus r. And the power series diverges for x such that s value of x minus a is bigger than r. That is for x greater than a plus r or x less than a minus r. The convergence at the endpoints of the interval when x minus a equals r, that's the ratio equals 1 case of the ratio test. To determine convergence or divergence at these 2 points, we determine that by substituting these values of x into the power series, then using techniques from sections 10 through 10.6 to determine the behavior of the series. So again, a lot of vocabulary here. Power series, radius of convergence, what it means to be a power series about A, and then the use of the absolute value, the sum of the absolute values of the terms of the power series, so we can use the ratio test. So work some problems with this and have fun. Bye.